let's do the homework for section 1.3. It covers the definition of continuity, finding the continuity of piecewise functions, and using the definition of, or using the intermediate value theorem. Okay, so our current objective here is to understand the definition of continuity. We're given a graph F, and we would like to know which statements are not true. Select all that apply. All right. Well, the function is defined at 1. The limit exists at 1, but it is not continuous at 1. So it is defined there. The limit exists there. Oh, I'm supposed to pick the ones that are not true. The limit is different from f of 1, and f is not continuous. I mean, f of 1 is -4. The limit towards 1 is -1. So it's not continuous. And the second option there is exactly the definition of what it means to be continuous. All right, this is a different objective. This is the objective of the intermediate value theorem. And all we got to do is count up the number of times that f switches between being negative and positive. You can see right here, between x equals 2 and x equals 3, f of x changes from being negative to positive. And since f is continuous, this is an important part. Since f is continuous, then we know that somewhere between 2 and 3, you are going to have a place where f is 0 because it's continuous. So you're going to have one of your zeros somewhere in here. You're going to have another one somewhere in here. And then a third one will be somewhere between 6 and 7. And then you have a fourth one and a fifth one between 8 and 9. So there are 5 zeros shown to us by the intermediate value theorem. Oh man, I clicked the wrong button. Okay. The graph is shown below. Which statements are not true? This function is not continuous. F of -3 also does not exist. So this is not true, and this is not true, and this is not true. Super. Find the smallest integer a such that the intermediate value theorem guarantees that f has a 0 on the interval from 0 to a. And the function I am given is 7x squared minus 8x minus 7. So here we are. There's my function. And what I need to do is just start with the first integer past 0, which would be 1. And let's check what is the sign of our function at f of 1. Well, actually, let me back up. First thing we should probably do is check the sign of our function at 0. How come? Because our interval starts at 0. So I want to know what is the sign of f of 0. Okay, well, f of 0 is negative because it's just going to come out to be -7, so that's negative. I'll be done if f of 1 is a positive number, because this would be, let's see, f of 1 is 7 minus 8 minus 7. Well, that's still negative. So I have to keep going. I need to keep going until I get a positive number. F of 2, that's going to be 28 minus 16 minus 7. And there we are. That is positive. I don't even care what it really adds up to. I just care about what its sign is. So, since we have that f of 1 is less than 0 is less than f of 2, since this is occurring, then by the intermediate value theorem, we are guaranteed the existence there exists some number c that lives inside of the interval from 1 to 2, such that f of c equals 0. That's probably a little more restrictive than what they were asking me for in the problem, because in the problem they wanted my lower interval to start at 0. And you can just, both f of 0 and f of 1 were negative, so it's just as sound of an argument to say this. Okay. Well then, the smallest integer that is going to do it is this 2, and that's my answer. On which of the following intervals does the intermediate value theorem guarantee that f has a 0? All right. Notice that these are open intervals, which is different from the statement of the intermediate value theorem in your notes. That's okay. Let's still just check the endpoints. That's the only thing we should concern ourselves with. So here is my function, and the first interval for us to try out is this one. So I want to check f of -5. I want to check f of 0. I want to know what the signs are. F of 0 is the easiest one to do because it's 3, so it's positive. Well, then I will know by intermediate value theorem that there's some point in here, I don't know what it is, but it would be in here, and it would cause f to be 0, and I would know that that would happen if this was negative. Well, is it? We would have -3 times 25. Ooh, that's a big negative number. That's -75. And then you add 3. That's negative. So somewhere here in between -5 and 0, there is a number that causes this expression to come out to be 0. So this is one of the answers. The next interval to check was from 0 to 3. Well, we already have that f of 0 is positive, so we know that f was a positive number on this interval. What happens at f of 3? F of 3 is a -3 times 9 plus 3. Again, this is negative. So we are guaranteed by the intermediate value theorem that some number between 0 and 3 is going to cause our function to evaluate to be 0. I mean, come on, y'all. That number is plus or minus 1, right? That's what the roots of this function are. And plus or minus 1 does in fact live in both this interval and this interval. So then, looking back at our question, these two work. This one here is not going to work, because both of those are going to give us negative quantities. F of 3 is, as we already know, negative, and f of 4 is just more negative because it's a -3 times 16, which is way negative, and then you add only 3. So it's still negative. It did not switch signs. It did not switch signs, so I am knowing that it did not switch signs, so I am not guaranteed that a 0 occurred on that interval. And point in fact, I actually know that there's no 0 on that interval. Understand the difference between being guaranteed that it's there by this theorem and the difference between the theorem guaranteeing that it's there and the idea that we are just unsure if it's there. Just because the continuous function was negative on both endpoints doesn't assert that there's no 0 there, right? If this was 3 and this was 4, then my function might start off being negative here, and it's going to be negative over there, but look, it has 2 zeros on the interval from 0 to 4. However, the intermediate value theorem could not guarantee for me that they were there because it didn't make the picture where it would start off as negative and then whoops, start off as negative and then wind up being positive. If it started off as negative and then wound up as positive, you are guaranteed for that to exist. But if they're both negative, we're not guaranteed anything, because we don't know that it didn't just go like this and stay negative the whole time. Here we are again. On which intervals does the intermediate value theorem guarantee for us that we have a 0? Okay, we've got 3 intervals to check. Here is the function, and the first interval to check was -5 up to -2. So I will check f of -5. And f of -5, come on, f of -5, I just want to know the sign. So that's going to be 3 times 25 minus 5 minus 1, that's positive. F of -2, that's going to be 3 times 9 minus 2 minus 1, that's positive. So there's no 0 guaranteed to us on that interval. What about from -5 to +4? Well, I already have the -5, so I just need to check f of 4. F of 4 comes out as 3 times 16 plus 4 minus 1. And we are once again positive. So no guarantee on that interval. What about the interval from 0 to 2? Well, f of 0 is -1, which is negative. And f of 2 is 3 times 4 plus 2 minus 1, which is positive. So we have a winner. We are guaranteed that there is a 0 on that interval. Given the graph of f below, which of the following statements are not true? All right, that hole is not filled in, so this function is not continuous. F of 3 does not exist. The limit exists. So which ones are not true? It's not defined at 3. If it's not defined at 3, then the limit, which does exist, cannot be f of 3. Consequently, it cannot be continuous. Which of the statements are not true? Well, this is just the worst case you could have. There's a jump discontinuity. It is defined at -4, but the limit does not exist. This is false. This is false, and this is false. Well, this looks like a test question. If I ever saw a test question on the homework, this sure looks like it. We have a piecewise function, and we need to know what value of k is it gonna take for this guy to be continuous. Okay, so here is our function. To be continuous, we need the left limit and the right limit to equal each other. If we can make them equal each other, then because of this part of the domain, so here, let me say it this way. The limit from the left deals with this part of the equation. So for sure, without doing any work, the limit as x goes to -2 from the left of this function is equal to f of -2. But that's only checking from one direction. We need to check from the other direction. Not just check, but force them to be equal. We declare that we need it to be true that as we approach -2 from the other side, that we have both of these equalities. If we can make that happen by judiciously choosing k, then this function will be continuous. Alrighty. This one was already true. It looks like I only need to focus on this part. Now f of -2 is using the top portion of the rule. So f of -2 is simply k plus 6 times -2. I want to force the condition that it is equal to the limit as x goes to -2 from the right. But whatever this thing is right here, as we approach -2 from the right, is a line. It is a linear equation. So its limit, because it is continuous, its limit is simply whatever you get when you plug in -2. This is the equation to solve for k. All right. So k minus 12 needs to equal a -2k plus 9. Add 2k plus 12 to both sides, and it just says 3k equals 21. So k must be 7. So k must be 7. If we choose k to be 7, then we will have a continuous function. It's continuous at everywhere away from 2, because this is a line and this is a line. Lines are polynomials. Polynomials are continuous. So everywhere away from 2, it's already continuous. And then by us choosing this number to be 7, we have guaranteed that it's continuous right where the domain breaks up, right at -2. Determine the value of k so that this piecewise function is continuous. All right. Here's going to be that function, k minus 5x, kx plus 7, and the first piece is on the domain less than or equal to -3, and this one is bigger than -3. If I just put them equal to each other, then this has the effect of saying that the two pieces adjoin. They join up. They're going to join up right at -3. Replace the x's with -3. I'm forcibly putting them equal to each other right when x is -3. Well, it should be a no-brainer that if I do that, I will be guaranteed that each piece comes out equal to the same y value when x is minus 3. The left side says k plus 15. The right side says minus 3k plus 7. So you add 4k minus 15 to both sides. You get 4k equals to 7 minus 15. And now we know that k must be minus 2.